So there are a lot of situations where some quantum system that you're interested in would be subjected to an external perturbation that is some function of time. And today we're going to talk about one method for understanding the physics of systems like that. So let's start with an example. So what I've drawn here is a hydrogen atom on the right, and we want to imagine that this hydrogen atom is just sitting there minding its own business um, when all of a sudden some electromagnetic wave comes along. So that's this guy, here it comes, and it's now interacting with the hydrogen atom, and it passes by, but the electric field is going to exert forces on the electron. And so from the point of view of the hydrogen atom, then we'll have a different Hamiltonian that turns on for a little while that electromagnetic wave is passing by. And so now we have some time-dependent physics, and we want to know what is the physical result of that. So before the electromagnetic wave passes by, we just have a hydrogen atom, and so that hydrogen atom electron is going to be in some particular state. Let's imagine it's the ground state. So that's what I've drawn here. We have this before picture where the electron is in the ground state of the hydrogen atom. Then the electromagnetic wave passes by, it interacts with the hydrogen atom, it goes away, and now afterwards, what we have is possibly some other state, and now it's still going to be some state of the hydrogen atom, because in the end, the Hamiltonian is back to what it was originally, but it might not be the ground state anymore. It might be some linear combination of various possible other states. And so let's draw the after picture in blue. So the after picture, it might look like a linear combination where you might have still some contribution from the ground state, but then maybe there's also some probability that you've made a transition up to some of these other states. And so your final state is going to be maybe some linear combination of the energy eigenstates of hydrogen. Maybe there's even some probability that the electron absorbed enough energy from this electromagnetic wave to leave the proton altogether, and so there could even be some part of the linear combination that would include a free electron. Okay. So time-dependent perturbation theory is a method that allows us to basically estimate this final state of a system, assuming that the time-dependent part of the Hamiltonian that turns on for some time and turns off is not too strong. It does not have a huge effect on the state. Okay. And so let's try to set this up. And so the setup is that we want to consider some quantum system, and let's imagine that that initial quantum system that we're thinking about is time independent, and it has some Hamiltonian that I'm going to call H0. Okay, and so this sounds a bit like the time-independent perturbation theory that we talked about before. And let's imagine that we also know the initial state. So initially in some state that I'll call psi of 0. Okay, and let's call that initial time 0, so at t equals 0. Okay, and now from the point of view of this quantum system, our external perturbation is going to be modeled by some extra term in the Hamiltonian that depends on time. Okay, so this is the big difference from the ordinary perturbation. Now we're going to add a term to the Hamiltonian that kind of is 0 up until a certain time, let's say t equals 0. Then it turns on, and it's on for a while, so the physics is different. That model, say the electron interacting with this electromagnetic field, for example, and then eventually the perturbation turns off, and we're back to the original Hamiltonian. Okay, so we turn on a small time-dependent perturbation, and I'm going to call that h prime of t, and let's assume that it turns on at time equals 0. Okay, so h prime of t is something that is 0 before t equals 0, and then it's non-zero for a while, and then we imagine that eventually it's 0 again. Okay. But what we want to do is understand what is the state, how is the state affected by this time-dependent perturbation? So we want to know what is the state at time t. Okay, now this could be a time while that interaction is still happening, or it could be a time after the interaction has turned off. Our method will allow us to answer both of those questions. So let's just talk about the general setup, and then in the next video we'll actually see how to solve our problem. And so what we want to do is first choose a basis to work in, and we will be working in the basis of energy eigenstates of our original Hamiltonian. So let's define psi n to be the eigenstates of, so these are the energy eigenstates of H0, and we will assume that those have energies that we'll call En. Okay, so we assume that we know what the energy eigenstates are for the original Hamiltonian, and we know what the energy eigenvalues are. Okay, and now we have some initial state, psi 0, but we know that we can expand that as a linear combination of these energy eigenstates. So let's write psi of 0, it's going to be some sum of Cn times psi n. Okay, and so we already solved the problem of what is the time evolution of that state in the case where we don't have a time-dependent perturbation. So if we just had h prime equals 0, so no time-dependent perturbation, then what we know is that psi of t is that same linear combination, but each energy eigenstate will evolve by multiplication with a phase. So we get Cn times e to the minus I En t over h bar, and then psi n. Okay. And so in particular, if we want to ask, like, what is the probability that if I measure the energy at time t, that I'll find the energy En, well, that's going to be independent of time. So that's the, so Pn of t equals just this combination. So the coefficient of our energy eigenstate all squared, and that's Cn squared, and that is independent of time. So if you start in the ground state, you're going to finish in the ground state. If you start in the third excited state, you're going to finish in that third excited state. And if you start in some linear combination, then the probabilities of finding the various energies won't change with time. Okay. Okay, so what about when we actually have the time-dependent perturbation? So what about if h prime is not equal to 0? So then we know that we can still write our state at any time as a linear combination of these energy eigenstates of h0. Those are a basis for the system. So even if we add a different term to our Hamiltonian, we can still work in that basis. And so I can write psi n as some linear combination, psi of t as some linear combination of the psi n's. And I'm going to do that in a particular way. So what I'll do is use almost exactly the expression from before, except now I will allow these CNs to depend on time. So it's going to be convenient when we're writing this to leave that phase there. We could have absorbed that into the CNs. We could have defined some other number, dn of t, to be that combination. But it'll be convenient mathematically to represent our state in that way. Okay. So because these Cn of t's are totally arbitrary so far, this still represents a completely general state of our quantum system. And so we know that it's always going to be possible to write our state at time t in this way. Okay, so for any t, there'll be some choices of these Cn's where the right-hand side will be the actual state. Okay. And so our goal with this time-dependent perturbation theory is that we want to find these coefficients Cn of t. When we do that, then we'll know exactly what our state is. And often what we're most interested in is calculating the probabilities for maybe moving to a different state. So we want to figure out, say, what are the probabilities Pn as a function of time, where if we measure the energy of this state at that time, we'll find the energy En. Okay, so back in our hydrogen atom example, maybe we start in the ground state. We have this small time-dependent perturbation when the electromagnetic wave goes by, and then we want to be able to calculate after some amount of time what is the probability that we've moved up to the 200 state, or the 300 state, or the 211 state. So in the next video, we will attack this problem mathematically using the technique of perturbation theory.